Imagine holding one of the simplest objects on your desk. It weighs less than a gram, costs only a fraction of a cent, and yet billions of them quietly keep the world's paperwork together every single year. But here's what nobody tells you. Behind that tiny paperclip lies a journey that begins deep inside the earth, travels across oceans, passes through roaring steel mills, and ends inside factories where machines move faster than the human eye can follow. Today, you're going behind the scenes to discover how an ordinary piece of bent wire becomes one of the most useful inventions ever created. Think about this. Every office, classroom, bank, hospital, and government building depends on these tiny clips. The world produces billions every year. Yet most people never stop to wonder how something so small can require such incredible engineering. And this is where the story becomes truly extraordinary, because everything begins with rocks that formed hundreds of millions of years ago beneath ancient mountains. The journey starts with high-quality iron ore mined in places like Australia's Pilbara region, Brazil's Carajás mine, Sweden's Kiruna mine, and Canada's Labrador Trough. These locations supply some of the richest iron ore on Earth, with premium deposits often containing more than 60% iron. Giant electric shovels dig thousands of tons every hour while haul trucks carrying more than 300 tons rumble across the landscape like moving buildings. Most people never imagine that a tiny paperclip begins in mines this enormous. After blasting and crushing, the iron ore travels through powerful magnetic separators that remove unwanted rock. The purified ore then gets crushed into fine particles before huge machines roll it into small pellets. These pellets make transportation easier and improve efficiency inside modern steel plants. Imagine millions of identical pellets moving along endless conveyor belts like rivers of red stone stretching toward the horizon. The pellets travel thousands of kilometers by freight trains and giant cargo ships before reaching steel mills around the world. Some shipments cross entire oceans, carrying hundreds of thousands of tons in a single voyage. Every shipment must stay dry and carefully monitored because moisture can reduce efficiency during steel production. What happens next surprised even experienced engineers, because the real transformation begins inside a furnace hotter than flowing lava. Inside an integrated steel plant, iron ore joins coke made from high-grade metallurgical coal and limestone that removes impurities. Together they enter a blast furnace reaching temperatures of nearly 2,000 degrees Celsius, or about 3,630 degrees Fahrenheit. The intense heat strips oxygen from the ore and leaves behind molten iron glowing brighter than the midday sun. The air vibrates with deep rumbling sounds while waves of heat shimmer across the factory floor. That molten iron doesn't become paper clips just yet. Steelmakers carefully add recycled steel and tiny amounts of carbon and manganese to create low-carbon steel with the flexibility needed for repeated bending. If the carbon level rises too high, the clip becomes brittle. Too little, and it loses its strength. This balance, measured within fractions of a percent, determines whether the finished clip will last for years or snap in seconds. Once the steel reaches the perfect composition, enormous continuous casting machines transform the glowing liquid into long steel billets. These billets cool under controlled conditions before rolling mills squeeze them into thinner and thinner rods. Every pass through the rollers increases precision until the steel measures only a few millimeters across. But here's the mystery. How does a perfectly straight steel wire become the familiar looping shape that everyone recognizes? That's where the real factory magic begins. The steel rods now enter a wire drawing machine, where the real transformation begins. Powerful motors pull the rod through a series of precision carbide dies, each one just a little smaller than the last. The steel stretches without breaking, shrinking from several millimeters down to about 0.8 to 1.2 millimeters in diameter. You hear a high-pitched metallic whine, smell warm machine oil, and watch the wire race forward at speeds that can exceed 15 meters per second. Drawing the wire creates tremendous friction, so engineers continuously cool and lubricate it with specialized emulsions. Without cooling, temperatures could climb high enough to weaken the steel and damage the dies. Sensors monitor every second of production while automated systems keep the wire perfectly centered. Most people never realize that a paperclip depends on precision measured in fractions of a millimeter. Next comes annealing, one of the most important steps in the entire process. The wire travels through a continuous furnace heated to approximately 700 to 760 degrees Celsius, or 1292 to 1400 degrees Fahrenheit, for several minutes before cooling under carefully controlled conditions. This heat relaxes the steel's internal stresses, making it flexible enough to bend without cracking. Imagine the wire glowing a dull cherry red as it glides silently through the furnace like a ribbon of light. After cooling, giant reels collect thousands of meters of finished wire. Robotic handling systems lift the heavy coils and feed them directly into high-speed forming machines. Every reel contains enough wire to produce hundreds of thousands of paper clips. But here's where the factory becomes almost impossible to believe, because the next machine bends wire faster than your eyes can follow. After cooling, giant reels collect thousands of meters of finished wire. Robotic handling systems lift the heavy coils and feed them directly into high-speed forming machines. Every reel contains enough wire to produce hundreds of thousands of paper clips. But here's where the factory becomes almost impossible to believe, because the next machine bends wire faster than your eyes can follow. Freshly formed clips immediately pass through vibrating conveyors that separate and align them. Powerful magnets remove any broken wire fragments while optical sensors count every single piece. Workers constantly monitor computer displays that track production rates, machine temperatures, and forming accuracy in real time. Every movement happens with incredible speed, yet every paperclip follows exactly the same path. Ohm paper clips receive an additional protective finish. Manufacturers may apply nickel or zinc coatings using electroplating tanks, where electric current bonds a thin metallic layer to the steel surface. This process improves corrosion resistance and creates the bright silver shine most people recognize instantly. The tanks bubble gently while polished clips emerge sparkling under powerful inspection lights. The finished clips dry in warm air systems before entering automated packaging lines. High-speed counters measure exact quantities, dropping them into boxes or clear plastic containers with astonishing precision. Conveyor belts never stop moving, and robotic packers stack finished cartons onto pallets ready for shipment around the world. But before even one box leaves the factory, every clip must survive a series of demanding quality tests, and some of those tests are far tougher than you might expect. Before a single paper clip reaches your desk, it enters a world of cameras, lasers, and artificial intelligence. As thousands of clips race along the conveyor every minute, high-speed vision systems capture hundreds of images each second. AI software compares every curve, bend, and length against a perfect digital model in real time. What looks like a simple piece of wire suddenly becomes a product measured with astonishing precision. Laser sensors measure the wire diameter and every bend with tolerances as tight as plus or minus 0.05 millimeters. If even one loop sits slightly out of position, powerful air jets instantly blow the defective clip into a rejection bin. The decision takes only a fraction of a second, much faster than any human could react. Most people never realize that a tiny office supply goes through the same level of inspection used for many precision industrial products. Engineers also test the strength of the steel itself. Special machines repeatedly bend paper clips open and closed to measure their flexibility and fatigue resistance. A properly manufactured clip should spring back without cracking during normal use, while weak samples reveal hidden problems inside the metal. You can hear the steady clicking of test machines as thousands of bending cycles push each sample to its limit. Some factories perform corrosion testing by placing coated paper clips inside controlled humidity chambers filled with warm moisture and fine salt mist. Hours or even days later, inspectors examine every surface for the smallest sign of rust or discoloration. Even a tiny defect can lead engineers back to adjust the coating process. What happens next surprises even experienced manufacturers because perfection leaves almost no room for error. Although robots handle most of the production, skilled technicians still perform the final visual inspection. Years of experience allow them to notice tiny imperfections that automated systems occasionally miss, especially unusual reflections, surface scratches, or subtle shape variations. Their trained eyes provide one final layer of confidence before packaging begins. It's a powerful reminder that human skill still plays a vital role alongside advanced technology. Factories continuously track production data using digital dashboards connected to hundreds of sensors across the manufacturing line. Every machine reports temperature, motor speed, vibration, production rate, and energy consumption in real time. If one measurement drifts outside its target, engineers receive an instant alert before small problems become expensive failures. Imagine an entire factory thinking ahead, correcting itself before anyone even notices something has changed. Only after passing every inspection do the paper clips receive approval for shipment. They leave the factory looking almost effortless, yet every single one represents mining, metallurgy, precision engineering, automation, and careful human judgment working together. But the journey isn't over yet. In the next chapter, you'll discover the astonishing numbers behind this tiny invention, the countries that produce most of the world's supply, and surprising facts that will completely change the way you see a simple paperclip. Now think about the scale. The world manufactures tens of billions of paperclips every year, with a global market worth hundreds of millions of US. China leads production by a wide margin, followed by countries such as India, the United States, Japan, and Germany, where highly automated factories supply offices, schools, and businesses across the globe. If you lined up just 1 year's production end to end, the chain would stretch around the earth many times over. A product so small has built a truly global industry. The story of the paperclip began in the late 19th century, when inventors searched for a simple way to hold papers together without damaging them. Over the decades, manufacturers transformed a handmade office accessory into a precision-engineered product produced at incredible speed. Today's factories create more clips in a single hour than early workshops could make in months. That quiet revolution happened without most of us ever noticing. Here's a surprising fact. A single high-speed production line can manufacture hundreds of thousands of paper clips during one work shift, all while maintaining remarkable consistency. Modern automation has reduced waste, improved energy efficiency, and made every clip more reliable than ever before. It's an extraordinary achievement hidden inside one of the simplest objects you use every day. Did you know that many paper clips contain recycled steel, giving old metal a completely new life? Did you know that some specialty paper clips receive colorful plastic coatings for organization and branding? And did you know that engineers continue developing smarter production systems that reduce energy use while increasing output? Even after more than a century, innovation never stops. Over the next decade, factories are expected to become even more intelligent. Artificial intelligence will optimize production in real time, predictive maintenance will reduce downtime, and advanced robotics will improve efficiency even further. At the same time, manufacturers continue searching for greener materials, cleaner energy, and lower carbon emissions without sacrificing quality. The future of the paperclip may look simple, but the technology behind it grows more advanced every year. From ancient iron ore buried beneath the Earth's surface to glowing steel, precision wire, lightning-fast machines, intelligent inspection systems, and finally the tiny clip resting on your desk, you've witnessed an engineering journey that almost nobody ever sees. Every bend represents decades of innovation, millions of dollars in technology, and the dedication of skilled workers around the world. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.